Hey, it's Sarah, and in this video I'm going to explain the integral. Now, to understand this concept, we need to talk about the two kinds of sums. The sum notation, which you might have seen as this, and the integral notation, which is this elongated s. An integral can be thought of as adding up a series of infinitesimally small pieces to find the total amount of something. And the sum notation is great for when we have discrete or separate things to add up. For example, when you write the sum of 1 over n from n equals 1 to 5, this is equivalent to saying 1 over 1 plus 1 over 2 plus 1 over 3 all the way until 1 over 5, which is what we're looking for. But what if we're dealing with something that isn't discrete? What if it's continuous, like a smooth curve? Now this is where integration comes handy. The process of finding integrals is called the integration, and it can be thought of as the opposite operation to differentiation. Imagine this, you're looking at a curve and you want to find the area under the curve. How would you do that? This curve isn't made up of neat separate blocks, it's smooth and continuous. So you could slice it up into infinitesimally small rectangles. Each of these rectangles has a width, let's call it dx, and a height, which is equivalent to the value of the function at that point. And by summing up all of these thin rectangles, because the width times the height gives us the area of the rectangle, you would get the total area under the curve. And mathematically, we can represent this as follows. This would give us a good approximation for the area, and as long as we're using a finite number, we could always say that we can just make our delta x's infinitesimally smaller and smaller, and we could get better and better approximations as the number of rectangles approaches infinity. And this idea of getting better and better approximations as we take the limit as n approaches infinity is the main idea behind the integral. There are two main types of integrals, the indefinite and the definite integral. The indefinite integral represents a family of functions and is the antiderivative of a given function. And it is written as the integral of f of x dx, where f of x is the function to be integrated and dx represents an infinitesimally small change in the x variable. The result of an indefinite integral is a function plus a constant of integration, usually denoted as c. For example, let's consider the function f of x is equal to x squared. To find the indefinite integral of this function, you would integrate f of x, which is x squared, with respect to x. And in order to integrate, we need to use the following formula. And using the following formula, we can calculate the integral for this polynomial. If you would like to see me derive this formula in a future video, please let me know. But for now, you're going to have to trust me on this one. And now we can calculate the final result for the integral of x squared dx. And it's really as simple as that. We use n equals 2, so we get x cubed at the top divided by 3 plus c, which is the constant of integration. Definite integrals are used to calculate the area under a curve that is bounded by 2 points on the x-axis. This is useful when you want to know the area under the curve in a specific region. And it is written as the integral from a to b of f of x dx, where a and b are the lower and upper bounds respectively. And the result of a definite integration is a number. So now let's use the same example as before, but now we have values for our limits of a and b, which is a is 1 and b is 3. And as we calculated before, the integral of x squared is x cubed over 3 plus the constant of integration c. In definite integrals, the constant of integration c does not appear because it cancels out when we evaluate the integral at our specific interval. When you evaluate a definite integral, the result is a number rather than a function, and there is no need to include the constant of integration. So all that's left to do now is evaluate the function at x equals 3 and x equals 1 and subtract them. This final value of 8 2/3 represents the area under the curve of f of x equals x squared, from x equals 1 to x equals 3. Integrals are used extensively in science and engineering and have a ton of real-world applications. For example, integrals are used to compute quantities like displacement, velocity, and acceleration. The area under the velocity time graph represents the displacement. And in biology and medicine, integrals help determine the concentration of drugs in the bloodstream over time in pharmacokinetics, where the area under the curve of this graph represents the overall drug exposure. Integrals are also used in modeling population growth in ecology and in medical imaging techniques like MRIs and CT scans. It's clear that integrals are not just some abstract concept confined to the realm of mathematics. Whether it's calculating the area under a curve or transforming complex data into clear images in MRI scans, integrals are at the heart of solving some of the most intriguing problems. So that's all for this video, and I'll see you next time.